So hi, my name is Remco. I have a slide deck full of complicated math over finite field equations, polynomials, roots of unity, and fast Fourier transform. However, this is not that slide deck. If you feel disappointed now, you're the kind of person we want to reach out to later. For the rest of you, I'm going to talk about how we actually use zero-knowledge proofs in practice in 0x right now to scale the decentralized exchange space. So first of all, why scaling? So right now, decentralized exchanges don't have a particular large volume. Crypto exchanges, however, already have more volume than any blockchain currently can feasibly handle. So if you want to decentralize the crypto space, you already need to look at serious scaling solutions. Obviously, we want more than that. If we want to tokenize real securities, we need to capture the volumes of traditional exchanges. That's another order of magnitude. If we actually want to democratize traditional securities and bring them to the people, you're more looking at the numbers that Visa and the other payment providers have. But you know what we're really after is tokenizing things like in-game assets, digital collectibles, all sorts of things that currently aren't even tradable at all. So this is the tokenized world scenario. This is what 0x is working for. We are building what we like to describe as the SMTP layer of digital exchange. So we're building an open source, free-for-all, standard protocol that people can use to trade with each other in a decentralized and trustless environment. So how do we scale this? Well, let's look first at scaling blockchains. This has been pretty much a known problem ever since, I don't know, couple of months after Bitcoin launched. It was clear that this wouldn't really scale to fulfill the goals of being the world's payment service. So ever since then, people have been thinking about this. The general consensus now on what sort of strategy we should employ for scaling blockchains is what we call layer 1 and layer 2. Layer 1 is scale the blockchain itself, make it handle more transactions. Layer 2 is try to make the blockchain do less. Design your decentralized applications such that they don't rely on the blockchain as much as that they currently do. So in the layer 1 category in Ethereum and related smart contract ecosystems, there's a bunch of projects, very credible efforts with incredibly smart people working on it for quite a while. But they seem to be converging to a number of strategies. The first and foremost one is sharding. Don't have every node try and redo every transaction in detail, but divide the work up in some way that is trustless and decentralized. Pruning, especially with state-based blockchains like Ethereum, you don't really need to keep the previous blocks around. You just need to make sure that you got to the current state in a trusted way. You don't necessarily need to keep the old states around like in the UTXO chain. State rent is basically changing the game. Right now you pay once up front to store something on the blockchain in Ethereum, and then it just sticks around forever. This mechanic doesn't reflect the underlying cost well, so it gets abused a bit. So we want to change this to a cost mechanic that encourages people to clean up after themselves, which will actually lead to a lot of interesting cascading changes in the DApp space once this gets accepted. Proof of stake in Casper and Light clients are more on a networking layer, like how do we offload the compute requirements of nodes and scale it that way. WASM is interesting. So for those familiar with Ethereum and smart contract programming, they know that Ethereum has this kind of funny and quirky virtual machine that uses these ridiculously wide registers. Meanwhile, the World Wide Web came up with WebAssembly, which is a virtual machine that has sort of similar goals to blockchain in the sense that it is a virtual machine that is able to safely process untrusted code. Where they differ is in that the web doesn't need to be deterministic, and crypto does. But WebAssembly people are interested enough in this use case, and the overlap is large enough that it actually makes sense to collaborate on this and create like this very fast, well understood, well developed virtual machine engine for use in smart contracts. So actually, if you look at all these 4 layer 1 scaling solutions, all of them are aiming to use WebAssembly as their core programming environment for scaling. And the other is, the last one here is zero knowledge proofs. I'm talking about things like Coda protocol when you apply it to layer 1, where instead of verifying every single transaction on every node, the first node who mines the block just creates a zero knowledge proof that this block was mined correctly, and then everyone just has to verify the proof. That is roughly the idea here. But that's about as much as I will say about layer 1, because this is more about layer 2. This is where you get things like Plasma Cache, Ignis Rollup, all those different solutions that have been going around for a while. And in particular, I will be talking about what ZeroX and Starkware have been developing together over the past couple of weeks, a solution we call StarkDex. Now let's get into layer 2 scaling. I like to divide layer 2 scaling solutions into 2 orthogonal axes, creating two different quadrants. So there's 2 main trade-offs that you can make here. The first is, are you going to keep your data on-chain? Or do you give up on that and move your data off-chain? The problem with keeping your data on-chain is that if you still need to store a little bit of data per transaction or do a little bit of processing per transaction, which means that you can at best get a factor improvement, but you cannot get asymptotic improvements this way. Rollup is an example of this. They use zero knowledge proofs in order to remove a lot of the computations there, but they still leave like the critical pieces of information of each transaction on chain for reasons of data availability that I will get into later. But the basic strategies that you can do here are compression, gas gulving, optimizing. It's a lot of fun. We do a lot of this at ZeroX already, but it's fairly limited in what you can do here. As soon as you cross this threshold, where you start storing data off-chain, it means that you only store a little concise message on-chain. So you would be using accumulators, miracle trees, vector commitments to just create a single root value that you store on-chain and leave the rest of it off-chain in nodes that you can query. Zero knowledge proofs are very amazing in this regard. Accumulators can only store a set data structure, so only set membership can be tested easily. Miracle trees are a little bit better in that regard, in that they have sort of an array interface. You have an index, and you can query the value stored at this index, which is very important when you're dealing with user balances, because you have a user ID that you want to map to a balance. Accumulators are not good for this. Miracle trees are good for this. Miracle trees are not super efficient though, because you still have logarithmic proof sizes in there. So people are working on vector commitments, which sort of combine the ideas of accumulators with the qualities of Merkle trees. But you can also like skip that whole development and go straight for zero knowledge proofs, because zero knowledge proofs allow you to do any kind of data structure and any sort of operation over it and create concise proofs that you did this correctly. So much for the data on-chain, off-chain discussion. The other thing, the other trade-off that gets made a lot is, do we want to use fraud proofs? So a lot of the, at least early Plasma solutions and Plasma Cache and the Plasma stuff that's out there right now, the way that it operates is that they create a Merkle tree of who the current owners are of the tokens in the system, and they only store the root of that on-chain. And then a bunch of transactions get processed, and then the root gets updated. And if you're watching this stuff on-chain and you don't trust it, because you haven't seen sufficient evidence to convince you that this was a valid state update, what you need to do is call the contract, call the blockchain, and say, hey, I don't trust this. This was a fraud. Please show me the evidence. And then you get into this back and forth game. But the basic idea of a fraud-proof mechanism is that whoever runs this scaling solution, which can be a bunch of decentralized people, is assumed to be honest unless proven fraudulent. So updates get accepted by the mainnet unless someone is able to prove that they were actually lying or misbehaving. Hence, this is called the fraud-proof approach. On the opposite end of the spectrum are honest-proof approaches, where the assumption is that whoever wants to do a state update is wrong unless they prove that they did the state update entirely according to the rules. So signature aggregation gets you some way in this direction, where you can just provide a single BLS signature that proves that all of these transactions were signed correctly. But again, if you really want to get the advantages, you need to look at zero knowledge proofs, because now you can do arbitrary computations and prove that you did them correctly. Like this entire state transition was done correctly. So for these reasons, take zero knowledge proofs and you get the best of, and in my opinion, the way to go is be in this quadrant, and with zero knowledge proofs, this is where you are. You'll get honest proofs of arbitrarily complex state transitions. You can use any kind of data structure and store it concisely. So this is the approach that we're taking at 0x as part of our general layer 2 scaling solution. So what we're talking about is the Stark batching part here. Besides that, we're also working on a peer-to-peer order book. So right now in the 0x protocol, we depend on HTTP JSON interfaces for the different relayers that are working on us for sharing order books with each other and sharing orders with each other. One thing we're working on, and we're working on this with libpeer-to-peer and protocol labs, is to create a generic peer-to-peer fabric where people can do this sort of off-chain communication for the DeFi space. Then there is trade execution coordination, which is essentially solving the transaction ordering problem, which is actually quite fun. The transaction ordering problem is not something Ethereum itself or any blockchain is particularly good at solving. They turn it into an auction where you put in your transactions and whoever bids the most transaction fees gets in first. So there's all sorts of funny front-running opportunities and things there. There's ways to solve them. You can create commit reveal schemes. You can create different application-specific logic in order to solve this. For example, in the case of 0x, we want to delay artificially certain kinds of transactions and give other kinds of transactions a slight advantage, and this will actually create a fairer marketplace. But these are not two parts of the whole system that I'm really talking about. The part that I'm talking about is what comes after we have this feed of ordered transactions. We are going to compress them using a zero knowledge proof and then submit them to the 0x contract on the Ethereum mainnet. So zero knowledge proofs. Brief recap. What you do is you have some function of a public input X and a private input Y, which has an output Z, not Y. And the proof is basically the claim that here are X and Z, so here is the public input and here is the public output. And I know, but I'm not going to tell you, of a Y such that this equation holds. So basically, I know the missing input to make this function go from this public input to this public output. And the cool thing about it is that you can really take any function you want here. Your limitation is basically the prover time, which is kind of bad. It is kind of like working on a really slow computer from the 1970s, with the difference that doing mathematical operations is pretty cheap, but branches are really expensive. They're not impossible, they're just very expensive. Same thing goes for comparisons and divisions usually. So that's the sort of framework that you're working in. But it's good enough that we have domain-specific programming languages that allow you to create this F function in Python-esque languages, implement things like SHA-256 in it, elliptic curve cryptography, that sort of thing is solvable. So one way to look at it is this private input. This is obviously the key distinguisher here. If there was no private input here, and you have X and Z, you can just recompute F for yourself. The cool thing, the unique thing is that you can hide part of the input and still prove it. And you can do two things with it. You can do privacy with it. You can store things that you don't want the receiver of the proof to know in the private input, but that's actually not the part I find most interesting. I find it way more interesting in that I can do the bulk of the input in this Y and just not tell you the rest. And the way it works out that, let's say X is, let's say 200 bytes of values, Y is a megabyte of transaction data, and Z is like another 200 bytes of updated state roots. That's super efficient scaling right there. So this is how we use zero knowledge proof to implement the scaling solution. F is the function that verifies transactions and update balances and some other stuff. The public input is a Merkle root of the old faults. Faults are what we call the tree of balances. So this is basically a hash of everyone's balances. And the old trade state, which means that, hey, these trades are still open, these trades have been consumed already, you cannot fill an order twice. This is something more specific to the decentralized exchange use case. And then there is some auxiliary public inputs having to do with deposits, withdrawals, escape hatches, as we will go into later. Now the Y here contains the full Merkle trees. So this F function can actually reconstruct the old fault root and verify that this Merkle tree was indeed correct. So now this function knows with cryptographic security that it actually has everyone's balances correctly. Then the rest of this public input contains all sorts of transactions. It knows the public keys because they're stored with the users in the vaults. It verifies all the signatures on all the transactions. It verifies that everyone has sufficient balances. It updates everyone's balances. And then it recreates the Merkle tree and outputs the new state root. So this is a super complex operation that is going on in this F function, involving constructing no less than 4 Merkle trees, verifying 2 signatures per transaction, updating balances, and right now the people at Stark were able to do this with more than 500 transactions in a single operation in, I think, a prover time of 25 minutes at the moment when we're shooting for 10. So this is pretty impressive, the amount of computation that you can do in this fairly adversarial computing environment. So yeah, out comes the new fault roots, the new state roots. So how do you use this in, so let's say we have the Ethereum blockchain here. We have our little contract inside each block, and the contract has a current state A. Now we receive a whole list of trade orders. We batch them together, apply them basically on the old root, get a new root. We prove this whole function, and the proof of this function gets submitted to the Ethereum blockchain. The smart contract verifies the entire start proof, which encodes the algorithm we just described, which basically encodes F, and that is done correctly. And when everything checks out, it will update the internal state of everyone's balances from A to B, and then the next batch gets submitted, and so on. So let's look a little bit more in detail in what is actually stored in the contract. The only thing that's really stored in the contract is the fault root and the trade root. 2 separate Merkle trees of depth around 32-ish at the moment. So the way it works is that the fault root is basically an array indexed by user ID and token. So let's say 20 bits user ID, 10 bits token ID, or we can kind of shovel it. It's not particularly relevant how we assign them, but basically it's a large array that has triplets containing a public key, a token ID, and a balance. So this is how we store how much each user, each public key, currently owns in the system and what kind of tokens that they own. Similarly, there is a trade route which at the moment basically stores a Boolean value whether a particular trade has occurred already or not. So if you have a transaction, then this is a signed message containing a unique unused trade ID, containing the public key of the maker of the transaction, the public key of the taker of the transaction, their respective token IDs, and the amount of each token that they wish to exchange with each other, combined with both of their signatures. This all gets verified, the tree gets updated. So that's a simple trade settlement transaction. There are 3 other kinds of transactions. So the first thing is a deposit. So how do you get your money from your wallet in the Ethereum mainnet into this system? At this point, it's kind of helpful, at least for a UX perspective, it's helpful to think of this as a sidechain. What we're basically doing is we're taking transactions, bundling them together in a block, and then submitting this block header to the Ethereum chain for verification. So what what you need to do in order to start trading on this sidechain is move your funds there. The way that works is that you move it to the contract. It is stored in the regular storage in this contract. The prover system notices that someone has a pending deposit, and in the next proof it includes an extra public input that says that, oh, I also accounted for this deposit. And it adds and it increments the balance of this user for this token. The smart contract sees it sees this public input, it verifies that indeed it has a pending deposit for this user for this amount, and if it all checks out, this pending deposit is removed, and now the new balance has this thing increased. The withdrawal mechanism is similar in the opposite direction. So what you do is you go to the sidechain, you sign a message stating that, hey, I want to withdraw these funds and move them back to the Ethereum mainnet. This message gets included in the proof itself. It results in an extra output, basically saying that, hey, this user wants to move these vaults out. Now the smart contract picks this up, this extra output, and relinquishes the funds to the original user. The escape hatch is a special case. It's kind of an emergency withdrawal. So as you noticed, in order to withdraw these funds, I needed to talk to whoever is generating these proofs. Now, hypothetically, this proof generating service can go offline and simply stop updating the state, stop providing new proofs. So what do you do now? This is where you can call the contract directly and tell the contract, hey, I have funds locked in this system and I want them out. I don't trust the system anymore. The contract remembers this. Now the prover service has some time to act upon it. So ideally, in the next proof that gets submitted, there will be an extra output. Yeah, I saw this emergency. I don't know what happened, but here is a proof of the funds of this, of all the funds of this user. Take them out. It's fine. And then the contract handles it, and the emergency is over. If, however, the prover is indeed malicious and ignores this request, and ignores it for some amount of time, let's say a couple of days, maybe a week, you can call the contract again and say, hey, you know, this emergency that I raised, nothing really happened, like this system is genuinely broken. The smart contract will now freeze the entire system. The latest state root will become permanent and unchangeable, and it goes into an end-of-life mode, where the only thing that you can do now is prove that you had prove that you own certain funds, and give this Merkle proof directly to the contract itself, bypassing this now defunct and ignored and and malicious prover system. The contract will keep track of who did this process already or not. There's obviously some optimizations in there to do this batch-wise, but this is generally the ultimate security that this system gives you, that even if the entire zero-knowledge proof part of the system becomes malicious, you can simply call it out on that, and you can still get your money out. Other security guarantees are not really necessary because the zero-knowledge proofs themselves guarantee that any mutation to your balance was signed by you. Just similar to how Ethereum works, where you need to sign for any transfer, that still holds true here. So, open challenges. This technology is very immature at the moment. There's not a lot of tooling available around SNARKs specifically, but in general, zero-knowledge proofs are still immature. I would say the recent Zcash CVE was an example of. I do think that the scaling use case has a significant advantage here, because if you're working on zero-knowledge privacy stuff, and it turns out that there are bugs or issues, it is really hard to just like manually mutate the system, compensate people who got lost, or even know if something was exploited in the first case. Whereas in a scaling scenario, you know what is going on, your system is always fully transparent and auditable, and you even have some sort of an option to fall back to a less scalable option if you really need to. And another thing right now, kind of due to the lack of technical maturity, is that yes, we can already do these really complex things around verifying double signatures on a single transaction, updating multiple balances in one go, and doing this for like a large batch of transactions. But a lot of other features are still hard to implement. When it comes to partially filling an order, which suddenly introduces rounding errors and complicates the math in these zero-knowledge proofs significantly, or going into even more sophisticated kind of auxiliary things that you would want a decentralized exchange to implement. So this is an active research area right now, like how can we implement these features inside the zero-knowledge proofs. This is where I think SNARKs do have an advantage though, where SNARKs are limited to quadratic arithmetic. SNARKs allow you to do higher order polynomials with pretty much the same ease, and this opens more doors. This is also kind of an open research area. How can you really leverage this fully? And I think there is a lot of room for improvement here, since this is a relatively new technology, and right now we haven't fully opened the doors yet to what it can do. Then there is the data availability problem. So if we use this escape hatch, in order for me to reclaim my funds, I need to have the Merkle proof that proves it back to the last state root. This Merkle proof updates with every block. So either I need to be online and very vigilant about it, or I'll be left with an outdated state root. This is a problem that holds for any off-chain data, off-chain scaling solution. They all have a data availability problem. And this is also the main reason why projects like Rollup choose not to go for the off-chain data route, and rather incur the penalty of not having like asymptotically better scaling. It's honestly a really interesting and meaningful trade-off. So the way we're solving this right now for the proof of concept that we're going to release this quarter is by simply having a committee of nodes that will receive the updated Merkle trees, and then each verify them and then sign off on the root hash. And all these signatures need to be submitted together with the zero-knowledge proof to the smart contract, and the smart contract will verify that the committee has signed off on this data being available. So now you've reduced your problem from having to trust that this data is available to at least one of these committee members being honest about it. And obviously on top of that, everyone is free to replicate this even further. I consider this kind of good enough for production, but it's not as decentralized as I'd like it to be. And this seems like an active area for research. It would be fun to use some of the technology that Filecoin has developed for data availability problems, for example, and see if we can reuse it. I know that Ethereum 2x has done some research around data availability in their sharding scenario, and there's some ideas going around using that for off-chain scaling solutions in an early version. Another one in the current proof of concept version is that the operator is still centralized, meaning that the proofs are generated and submitted by a single entity, and there is no open way of participating in that. The way the system works, though, means that the risk associated with the centralization is very low. Like the transactions are already ordered, and the zero knowledge proof pretty much guarantees that this operator has to act honestly. But there's still some issues around censorship, for example. So we ideally would want a system that allows the operator to fail over to a new operator, or decentralizes it, or turns it more into a mining pool where anyone who wants can contribute here. Wallet support. So all of this is still fairly technical and fairly low-level stuff. We want to push this to the users. So the proof of concept this quarter is going to be about the technical details. We want to actually show that you can do SNARKs right now on Ethereum mainnet. It's going to be launched on testnet, but circumstances are the same. And honestly, I'm quite excited that we can already tell you that yes, this is definitely going to work. You can do SNARKs right now in EVM. You don't need to pre-compile. That's how cool they are. But going from a proof of concept to a full-fledged production quality system means that we need wallet integration, we need user interfaces around it. And the wallet integration is particularly tricky because these SNARKs, by their nature, require different elliptic curves. You can't use the SECP256K1 curve that Ethereum uses. You need to develop your custom signature algorithms around it. Wallets need to somehow support this. And then longer term, there's a very interesting challenge in, so you have this sidechain now. Right now, this sidechain can barely run a decentralized exchange. We will add more features and make it like a more full-fledged, feature-complete decentralized exchange. But that would still be, that will bring us on the level of Stellar, and we want to be at the level at Ethereum. We want to have an open ecosystem where anyone can build, where like the whole DeFi space can live and grow and develop the tools. Part of what made 0x as it is currently on Ethereum mainnet so awesome is that all these projects came along and implemented these complicated protocols on top of 0x that we didn't even imagine possible, but it adds so much value. And this is where you get the real network effects. So recreating this in layer 2 scaling solutions is going to be really hard, especially if everyone is shooting for creating these kind of project-specific sidechains where you need to move funds through, and if all the interactions still have to go through the Ethereum mainnet, this kind of kills the interaction and performance bonus that you would get. So designing, like collaborating with the wider community and designing open protocols to do this, that's one of the more interesting open challenges here. So there's also a couple of proposals that we're working on right now. This kind of goes back to some of the issues we run into and advice we have for layer 1, for Ethereum itself. One of the things we notice is that the ratio of the cost of transaction data versus on-chain storage is actually quite detrimental to layer 2 scaling solutions right now. If you have, let's say that, forget the zero knowledge proof part for the moment. Let's say I just want to store a Merkle root of people's balances and keep that updated. In theory, that would require me one storage slot. But now every time I want to access a balance on-chain, I need to submit let's say roughly 32 values of a Merkle proof in order to get to that person's balance. Now the funny thing is in Ethereum right now, submitting 32 values of Merkle proof in a transaction costs you about 70,000 gas in transaction size, whereas a storage slot only costs you 5,000 gas. So this trade-off is not favorable towards off-chain scaling at the moment. Another is that, like I mentioned, we need custom elliptic curves. Ethereum natively only supports one particular curve, so creating a precompile for arbitrary elliptic curves would help a lot of projects. This is also a nice opportunity to try EWASM. So one of the ideas for ETH1X is to no longer specify precompiles and have every every client developer implement them individually, but leverage all the work that's been done in EWASM and allow the community to vote on a WebAssembly blob that will get included as a next precompile. This is kind of a nice trade-off between having a full-fledged EWASM chain running that 2.0 will do, but getting some of those benefits earlier, but not go hard on untrusted code yet. Like have community vetted code be included. So I hope this will lead to more precompiles being added to ETH1X. Similarly to these elliptic curves on chain, we need the wallet support, like I mentioned. I wrote a proposal to create a WebAssembly extendable API for wallets such that they can accept DApp-specific cryptography in a secure way and run it. WebAssembly itself can also be extended to better support different cryptographic primitives. Add carry, full-length multiplications or carryless multiplications are some instructions that we can likely, as a blockchain community, talk to them about. I've been talking with Mozilla about it, and they seem actually, they're kind of like, where is the Ethereum community? We used to hang out with them. They're not around anymore. There's some good ideas there. We'd love to meet these guys again. And they like these ideas. Like, we should do a better job interacting with the wider WebAssembly community. They like this stuff. They want to see, they want to help us out, and they want to see this included. Similarly, this proposal for wallets, it actually makes sense to propose this to the web crypto standard itself, which would be really awesome. Anyway, that's sort of the proposals I'm working on right now. Again, my name is Remco. I work at ZeroX, and we're currently hiring people to further research zero-knowledge proofs and how you can leverage the unique advantages of SNARKs to create more complex systems or solve some of the larger problems of doing like hard computations, difficult computations inside a zero-knowledge mathematical environment. We're looking for cryptographers to implement these precompiles, wallet extensions, and the zero-knowledge proof stuff itself. And we're looking for protocol engineers to design things like these deposit withdrawal games, escape mechanisms, data availability problems, and so on. Thank you. All right, I think now we go to the coding session, right?
Yes.